which is it just told me it was recording in progress. So he's going to talk about a different architecture for studying responses on a continuous scale. And at some point, we've got to compare the models, but we haven't got to it yet. We're still developing them. So most tasks studied in cognitive psychology involve two or maybe confidence judgments, a few of response alternatives, and use button presses because they're easier to record from. You could use speech, but then you need speech recognition or somebody to write down the responses. So buttons are what's usually used. So I'm going to present a model that was published in 2018, I think, data from 2 tasks that are similar to visual working memory, and then I present data and fits for 4 visual working memory experiments. So the first task, we get a color stimulus presented centrally, and the task is to move the eyes or point to a position on a color wheel response circle around the stimulus. In the second task, you get a 2-digit number, and you have to respond by moving the finger to a point on a number line, say 1 to 100, that corresponds to the number. So these number line tasks are important because they're used in examining development of numeracy in children. They appear to predict later development, later achievement and numerosity and numeracy. And there's a lot of sort of controversy about that. Number line tasks are used extensively in teaching. If you type in number line to Google search, you'll find all kinds of things. They're useful for model development because the stimuli have well-defined ordinal relationships and mappings to response scales. And up to this point, 2-choice tests have been more popular, but in real life, we make a lot of responses on continuous scales. And so the idea is to start modeling these. So here's the first task. You get an array of pixels on the screen, and you have to point to the dominant color or move your eyes to the dominant color, which might be sort of reddish here. The number line task, you get a 2-digit number here, your finger is resting here, and you have to point to the position on the screen that corresponds to the 2-digit number. So there are some tricky aspects of these designs. What you don't want is people making the decision while their finger or eye are in motion. So the idea is you get subjects to hold their finger, say, I'll talk about touchscreen, on the square at the bottom, and hold it there until they've made the decision, and then move their finger quickly. So make it a ballistic movement. So if movement time is too long, you give them a warning message. If they lift the finger too quickly, you get a warning message. If the response is longer than an upper limit, you get a warning message. And you give accuracy feedback if the response is near the correct position, and an error feedback is 0 if it's not. And the values of these timings are task dependent. If you're making mouse responses, they're a lot slower than eye movements. And then you've got to look at the apparatus. So our touch screen, we had a delay in 110 milliseconds detecting a lift, and 48 millisecond delay in detecting a press. And you have to measure those and take them into account if you care about the absolute values of reaction time. There are different ways to do this. The easier way is to get a video camera, 16 millisecond frames, and just video what a stimulus coming on, a finger press, and then when the system detects the response. So that can be pretty fun doing this. You can also do it with a photodiode and an oscilloscope, but I'm not sure people have oscilloscopes these days. All right, so the data. We examine choice proportions at all locations on the response circle or line. So this might be on a scale on the bottom here in this little figure of 360 degrees. The model predicts how responses are distributed over locations. However, in the tails, the C areas, you might not get a lot of information about reaction time. So we group responses to provide enough data for distributions. So in the color task, we group responses around the peak, we group them in the lobes around the peak, and then we group them in the tails. So we get 3 areas essentially. And then we can get choice proportions and reaction time quantiles for doing model fitting and displays of the fits. And then we go back and present fits of accuracy, well, the choices, proportion of choices as a function of angle and reaction times across the whole range. So this is used to do fitting, and then we can go back and look at the original fits. So this model assumes continuously distributed stimulus representation and continuously distributed noise, and these are accumulated over time to a decision criterion. So the idea is we get stimulus encoding, we get a distributed stimulus representation on the dimension. So if this was a number line, we would have 0 to 99. If it was a color, we might have 0 to 360 degrees. So this can also be viewed in neuroscience as a population code. And I worked with population codes. If you go back and look at a 1981 paper, I essentially have population code model there for a simple matching task. Okay, so then we have evidence accumulation. So we have this distribution along with noise accumulated up to a decision criterion. I'll tell you what this noise is in a moment. It's essentially spatially continuously distributed Gaussian process noise. So that noise plus signal is accumulated until you hit a decision criterion. And then you get a response output. And the encoding time, response output time is the non-decision time, which is added to the decision time from the accumulation process. So the stimulus representation is distributed over angle or number like this. We have trial-to-trial variability in the height of this distribution. The noise plus the stimulus is accumulated until some point on this function hits the decision criterion. We also have trial-to-trial variability in the decision criterion. So all these parameters in the model, I won't talk about them because you have to read the paper, but just note that all these kinds of variabilities are in the model. Now, the model assumes that noisy evidence is accumulated over time, and the key to the model is how we represent noise. It's a Gaussian process. This is a spatially continuous random variable in which the distribution is Gaussian at any spatial position. So at any angle, if you look at samples, it's normally distributed. And the values at nearby spatial locations are correlated. The way you make this is by generating random values, random normally distributed numbers, and then smooth them across the spatial dimension. This is like a Gaussian smoothing. Turns out this is in signal processing and electrical engineering. I studied this way back when I was doing physics, looking at signals going up to satellites and coming back through noise in the atmosphere. I wasn't actually working on that. I took a course in it and didn't do very well, but now I understand it. So here are examples of random samples of Gaussian noise. In any vertical dimension, the distribution is normal. And you can see that there's correlations because if you're high at one point, you're likely to be high at nearby points, and then the correlation dies away. And the correlation is a function of this parameter R. This is the relative size of noise and signal to fit data. The noise has to have a higher variability than the signal for that to work. In the number line task, if we have the number 5, the stimulus is distributed like this, the stimulus is 35 like that, 55 like that, so on. So these are examples of the drift rate distribution for the number line task. These are for number line tasks, but if we rescale the x-axis, they could be for the color task. Here are examples of evidence accumulation. So here we get evidence accumulation, we have the criterion here, but there's a big negative going peak here at about 11. Here we get another one that ended in 29 time steps. There's a big negative peak at about 5. There's a negative peak at 85. There's no negative peak at 85. It turns out that if you add random Gaussian numbers together, you'll get peaks and you get troughs, and these troughs will occur just randomly. I should also add in the model that the evidence is normalized to 0 on every time step. So the total amount of evidence stays at 0, it's control of 0. So if something goes up, something else has to go down. All right, fitting the model to data. What I do is generate simulated data from the model with parameters that are somewhere near ones that fit the data. I get the 0.13579 RT quantile reaction times for the different stimulus groups. So in the color task, it was the A, B, and C groups. Then I adjust the model parameters so the areas between the quantiles in the model match the differences between the quantiles in the data. So 0.1, there's 0.1 probability below that, 0.2 between the two, 0.2 between the next two, and so on. And then I display fits by showing quantile reaction times, and I'm plotting each subject and each condition. And then I'm going to display the distributions of responses and reaction time over position. So this here shows any misfit for any subject and data. And I've taken to doing this a lot of the time because it really exposes what the fits are like. We're not hiding a subject or a condition in some other summary statistic. One thing that I'm seeing now in a lot of papers is summary statistics, so you don't actually know what's going on in the data. You don't know if the model actually fit the data. So when you read a paper, you want to see, did the model fit the data? Did it fit it for each subject? And we can also compute error bars using bootstrap methods. I'll go to that. So for the eye movement responses, red patch, maybe move to the red area. Here's what we get in terms of response proportions. So we get a reasonably good match. So what we're plotting is the response proportion on the x-axis for these A, B, and C areas, and the theory on the y-axis. The 0.1 quantile reaction time is the leading edge. The 0.5 is the median, and the 0.9 is the tail. These are the error bars from bootstrap method, the maximum and minimum, and here's 2 standard deviations in the data. Remember, the data's on the x-axis. You'll see there's a misfit here. The model, the data are giving 0 responses. The model is saying there's a small response probability, maybe 5%. So this is about the only significant misfit. Of course, you're going to get responses from single subjects for some of the conditions all over the place. Here are the model and response proportions. So in the data, we had the proportion of, say, red pixels in that example is 35%, 20%, 10%. So here we vary difficulty going down the screen, and we get the model distribution over angle and the data over angle. And you can see the fits aren't quite perfect. This isn't quite wide enough, but the fits really mirror. The peaks go down at about the same rate and the tails increase in the same kind of way. So all this stuff is from the 2018 paper. Now we look at reaction times, and the surprising thing is that reaction time is constant across angle. Here it changes. The mean, this is the area in which there are most responses in the middle. So these are more variable because there are very few responses. But you can see the reaction time here is about 500 milliseconds, and it jumps up to about 650 for the difficult stimulus. So we're getting difference in reaction time as a function of difficulty, but we're not getting much difference in terms of distribution across angle. And that's because it seems to me all angles are roughly equally probable when you're doing it without seeing the stimulus. And so you have the same decision criterion, and the model predicts that the distribution across angle is relatively constant. The data look like that. In the other experiments, they're also pretty constant. So this is kind of a surprising thing. People might have said the data go up, and in some tests they do. But when I fit the model, I really couldn't believe it. The model said the data are flat. So that was pretty cool. You make a prediction about nothing happening, and nothing happens in the data when you expected it would. The number line task, I'll just skip through this. So this is the idea to show that it handles results on a number of different kinds of tasks. So here we get the proportion of responses. The 0.1 quantile reaction time, the 0.5, the 0.9, these all show pretty good fits. And remember, this is for every subject and every condition in the experiment. Here are what the data say. So if you're asked to say, where is 15 and point to it, 60% of the time, you're pretty near the peak within a range of about 2.5 on either side. And then this drops down as you move away. So when 15 is presented, they don't say 95 was the answer. When you're in the middle of the range, say 45, you can see the spread is wider. And then it becomes narrower as you move to the edges. So there are these edge effects. And this is what the model predicts in terms of choice proportions. And if you think that I just copied the graph, I didn't actually, because the 4 and the 5 here don't overlap here, but they overlap there. In other words, the data are very regular and the model captures that regularity. Median reaction times, again, are pretty much flat. Because there are very few responses outside the central ranges around the number, the data are kind of constrained. And the model does miss a little bit in predicting that the ends are faster than the middles, but all in all, it's not too bad. So these are related models. The model I said earlier, the overlap model, which we applied to a number of reading tasks in which you present a letter string and you have to say same or different for another letter string presented after. The distributed representation is used in the RT-Con2 confidence model. And this relates to population code models and dynamical system models. It's a genuinely continuous model across time and space. The standard diffusion model uses continuous space, time, and discrete number of responses. This model produces behavior qualitatively similar to the two-choice model, reaction time distribution shape, and it fits distributions of responses across the horizontal range and reaction times for correct and error responses and their distributions. So I think it opens a new domain of study. But a warning, fitting the model is slow and you've got to tune it for parallel processing, and that can be a bit complicated. So I've got it down to fitting a subject in a couple of minutes, like 5 or 10 minutes. But that's using a 64-core processor and using a highly tuned language, Fortran, very old language, but you can really tune the hell out of it. If you tried to do this in Python, you'd probably be waiting for days. And the model fits at least as well as shown in the figures, and it's sort of like a benchmark. So now as this field develops, the models can improve, but I've shown you what the model can do, what this version of the model can do. Maybe other versions might do better. All right, so now what we've done is taken that and applied this to the visual working memory task. The visual working memory task goes like this. You present some colored squares, then they're erased. Then you present a color wheel and outlines of the squares. So one of the squares gets outlined, but it's white inside or no color inside. You have the color wheel, and now you have to point or move your eyes to position on the color wheel that corresponds to the color that was in the square. You can imagine that if the 6 squares there, you might know something about some of them, but you don't know anything about some of the others. The response, and we've got experiments with finger, eye, or mouse movement to the position of the wheel that corresponds to the color that was in the square. So we have parameters of the model, and I'll go through the models in a minute. I don't think we need to do this. Well, let's just do this. We have drift rate distributions for the different set sizes. This is the number of squares in the color wheel, 2, 4, and 6. We have probability of guessing for set sizes 2, 4, and 6. And then we have criteria that could be the same or vary. We have models in which they're fixed, in which they're there are different criterion settings for each set size. So let's go through the models. And these are sort of taken out of the visual working memory literature. So we have a discrete model. It says that drift rate is constant for all set sizes. So you've got the same drift rate. And in this model, you can have guessing. Guessing is 0 for set sizes less than capacity. You have full information. And then when set size goes over capacity, you're allowed to guess. Well, the model is allowed to guess. There's a discrete hybrid model that says drift rate varies as a function of set size under capacity and then is constant over capacity. So V for 2 items is smaller than V for 4 and 6. Probability of guessing is 0 for set size 2 in this model, less than capacity, and varies as a function of set size over capacity. Resource-based model says there are no guessing, and drift rate varies as a function of set size. So this just assumes the height of the drift rate distribution varies with set size. Then we added a resource plus guessing, where VI varies as a function of set size, and probability of guessing varies as a function of set size. And then what we're going to do is compare these models in fits to data. So how do we account for guessing? Well, we assume there's no information and the same process runs as when you have stimulus information, and our probability of guessing is like this. And for set size 6, the probability of guessing in the models goes up to about 40%. In other words, for 4 of the items in a set size of 6, you have information that tells you about the stimulus. And for 2 of the items, you have no knowledge at all. So this makes 4 models, and we add 4 more models in which the decision criteria differ across set sizes. We fit the model in exactly the same way as for the earlier tasks, and we summarize them in A, B, and T regions. The next plots are for a touchscreen experiment. The plots from the other experiments are similar, and I can show a PDF or a paper in those. Remember, we're fitting response proportions and distributions for each subject separately. Dale, I haven't turned that on. Okay.
The monitor or the computer?
Computer. Yeah. So here are the different models. Discrete model with 3 criteria. Discrete hybrid with 3 criteria. Resource-based model with 3 criteria. Resource-based with guessing, and resource with guessing with 3 criteria. So the discrete model, if you look at the spread of the axis, so these are for every subject and every condition. So the conditions are A, B, and C regions around the central peak, and then for 3 difficulty conditions and 16 subjects. And you can see there's a spread of misses in the proportions. The quantiles aren't that bad for the 0.1, the 0.5, and 0.9 quantile reaction times. If we add 3 criteria, that doesn't help. The discrete hybrid still has some misses, but when we let the probability, the drift rate distribution differ for set size 2 versus 4 and 6, and we have guessing for set sizes 2 and 6, we actually get a pretty reasonable fit of the model to data. The resource space, where all that varies is the height of the drift rate distribution, not great fits. With 3 criteria, somewhat better. When we add guessing, the model actually improves and we get reasonable fits. So here are the models, here's the data, and what you've got to do is compare the data with the models. And let's just go to the 2 leading models. Discrete hybrid, it gets the height of the peak and it gets the tail. And say for set size 6, so this is set size 2 across here, 4 in the middle and 6 at the bottom. Here we get reasonable matches to the proportion of responses in the tails. And the resource plus guessing is about the same. We get probability in the tails about the same and the peak about the same as the data. So here we're matching things reasonably well. And reaction times, again, in this task, there's not much change. And this is for touchscreen task. There's not much change across angle, response angle for the choice. And in fact, there's not much change in reaction time vertically either across the set size 2, 4, or 6 conditions. And these models predict reasonably flat reaction times in just the same way. Now remember, we have skewed reaction time distributions and the models are capturing those. All right, so we can do a model comparison with AIC and BIC, and we get the discrete hybrid fits best. So this is touchscreen, eye movement, mouse movement, and experiment 4 is one where we had 5 subjects for something like 6 sessions each, and there the resource-based model does better, but it's not that much better than the discrete hybrid. 3 subjects are fit by this model better, 2 by this. The thing in parentheses says the number of subjects that are best fit by the models. And for BIC, we get about the same. The number of subjects better fit by the model, the average BIC value. If we let the criteria change, so in experiments 1, 2, 3, there are 3 criteria, and experiment 4 only had set sizes 2 and 4, so there are 2 criteria. Again, we get the discrete hybrid and the resource-based with guessing doing about the best fits. For G squared, we get a change in the value from the discrete model down to the best fitting models of quite a large change in the values. So the absolute fit actually improves a lot, going down from the worst models to the best models. If we look at what happens to criteria, the criteria go down a little bit as you go to larger set sizes. So it's as though they try harder for set size 2 and then say, well, this is set size 6, I don't have to try so hard. Don't have to accumulate so much. There's a nice post hoc explanation of that. For the drift rates go down by about half. And you can see that the 2 leading models, the discrete hybrid and the resource-based plus guessing, aren't saying 2 things that are too much different. The difference in the resource-based where V can vary is 2.5. Here, it sits about in the model. And the guessing parameter is kind of similar across these models. The probability of guessing at set size 2 is very, very low in the resource-based model. It's a little lower in the resource-based model here, 40%. Right, so we also tried letting the standard deviation in the drift rate distribution change instead of the height, going from set sizes 2, 4, 6. The fits were just a little bit worse. This is a big deal in the visual working memory literature. And for the guessing models, we're around 0.4. The probability of guessing was around 0.4. So this, I think, opens up this field of visual working memory to look at reaction time. The area of research has gone on for about 20 years now, just looking at choice proportions. And the various models mimic each other. I think what happens here is, once you have to account for reaction times, you have to have guessing. A model with just the height of the distribution or the width of the distribution changing, resource-based model just won't fit. This model accounts for choice proportions and distributions. And the difference between these 2 models, they fit about the same. If you looked at the AIC and BIC values, there was a difference between V4 and V6. Those are the drift rates for set size 4 and 6, but it wasn't that large. The value of guessing for set size 2 in the resource-based model was close to 0. So essentially, it means the best fitting discrete hybrid and resource-based models both had guessing. And other than the small difference in drift rate difference, they were essentially the same model. So within this framework that deals with reaction times, the results converge on a common model that has drift rate changing with set size and has guessing. So it sort of starts to resolve. If you believe this model, it resolves the issue that's plagued this, whether there's guessing or not, whether distribution change or not, what the kind of model is. It's much easier to fit accuracy alone, choice proportions, the distribution of choice alone, than it is to fit that plus reaction time. Okay, so that was one talk. And now I want to talk about something completely different using the two-choice decision model. And this is a clinical application. And I'll get to why clinical applications are important now. Incidentally, the previous director of NIMH, National Institute of Mental Health, about 15 or 20 years ago, pulled most of the money out of cognitive psychology and denoted it and moved it to brain imaging kind of studies and genetics. And now he admits that that was probably a mistake. But I'll talk about that, and maybe we can discuss why it may not have been a mistake later. So, two-choice diffusion model, many of you know this, noisy accumulation of evidence towards one of two decision criteria. We explain accuracy in the distributions of correct and error reaction times. And what I'm going to do is briefly describe some older work and parameters of the model change across age and how memory changes with age. It can be pretty depressing. And then I present results from memory disordered patients. These are mild cognitive impairment and Alzheimer's, and how well model parameters allow us to discriminate patients from controls. So this is a real application. So it's been applied in a wide range of things. So modern cognition and modeling has had almost no impact on clinical practice and neuropsychological testing. If you look, I got something online, Committee on Psychological Testing, Validity Testing for the Social Security Administration, blah, 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 2015. And Medicare price data, Medicare spends about $800 million a year on psychological testing. It also spends on grants from NIH over the years on psychological testing. Now, if you go and look at neuropsychological testing, modern methods and models have had no impact for 30 years. If you go look at what is working memory is performance on these tests. There's speed of processing, which is how quickly you can do some tests. No mention of accuracy and reaction time and how all these things relate to each other. It's totally dismal. If our field is going along and not impacting this domain, it really is an indictment of our field. We have to get into this somehow. So I'm going to assume that most of you know about this kind of model, noisy accumulation evidence up to two criteria. To examine the effects of aging, we're going to focus on three parameters. Boundary separation, that's how much evidence you need to make a decision. Non-decision time, which is the amount of time you encode the stimulus, say extract memory information, and then response output. And then drift rate, which is the quality of evidence that's extracted from the stimulus, and if it's a memory task, from memory. We fit the model to accuracy, correct and error reaction time distributions across conditions, and it produces values of these components of processing. And we're going to look at decision criteria, that's the separation of these. Non-decision time is the time for everything except the decision process. And evidence, which is how quickly you move up towards this boundary or down towards that boundary. This is important, and people who don't do modeling don't understand it. Unlike a lot of models in cognitive psychology, dual process and signal detection models, which are applied to, say, single processes, the model is testable. If it doesn't fit the data, the model is invalid. Dual process models often take two data points, say something in an include and exclude condition, get familiarity and recollection. You're taking two data points, transforming to two model parameters, and so the model isn't testable at all. the model fits perfectly and there's no check on whether the model is the correct description of processing. So I'm going to talk about two experiments in one study, recognition memory. So what you do is you have words that are high and low frequency in English. This is with English subjects. Study a list of words, then get a test list. And to each item in the test list, you say whether it was studied or new. So each test item, you say studied or new. Very simple. Lexical decision, you get a letter string and you respond whether the letter string is a word or a non-word. The words are high, low, or very low frequency words in English, and the non-words are pseudo words, English-like non-words. So in aging, we find older subjects have wider boundary separation than young subjects. They have larger non-decision time. But in these two tasks, recognition or lexical decision, they don't have lower values of drift rate. So recognition, memory, and lexical decision are preserved until, even 75 to 90. But what we find is very large effects, 2 to 1 on drift rate with IQ. So people with higher IQs, as measured with standard IQ tests, have higher drift rates than those with lower IQs. And boundary separation and non-decision time do not change with IQ. But if we go to associative recognition, and associative recognition subjects study pairs of words, and then they get a test pair and have to say whether the two words were in the same pair or not, performance falls very quickly with age. So if you're old and you have to remember that two things go together, write it down because you won't remember it. Individual differences, accuracy and mean reaction times correlate across tasks. Drift rates correlate across tasks, boundary separation correlates across tasks, and non-decision times correlate to tasks. So if a subject is good at one of these, has a high value of this on one test, they have a high value on the other. And in the memory test, we find that cued recall, free recall, drift rates for item and associative recognition correlate. So if memory is good on one of these tests, it's good on the others. And this changes when you get up to 75 to 90-year-old because performance in associative recognition and cued recalls tend to go to 0. Drift rates correlates for lexical decision and recognition across all age groups. So this is important because if you're going to look at neuropsych testing and see if some subject has an abnormal score from others, you need a model that can handle individual differences. This model does. So the aim of the study that just came out in JP General is to examine item recognition and lexical decision for memory disordered patients. That's Alzheimer's and MCI, mild cognitive impairment. About 10% of mild cognitive impairment transition to Alzheimer's every year. So we see if the diffusion model can fit the data and what changes between memory disordered patients and controls. And then we want to see if diffusion model parameters can use to discriminate between memory disordered and control patients. So the memory disordered patients are tested for 15 minutes of lexical decision and 25 to 30 minutes of recognition. The patients are diagnosed in a memory disorders clinic by neurologists. So this is important. This is sort of like the gold standard. You can't do any better than this. You could run neuropsych tests, but those aren't very accurate. The memory disorders, it's about a 3-hour evaluation. They run various tests. They talk to caregivers. They ask standard behavior. Do you forget things? Do you know where this is? Do you know where that is? There's a lot of interaction in this. We have 105 memory disordered patients and 57 older adults. And these are tested in exactly the same way, like in a clinical trial. You can't change things as you go through the experiment. So here's what happens to model parameters. Memory disorders, older adults, recognition, boundary separation goes up, non-decision time goes up, drift rate goes down massively for recognition, which is what you'd expect. Memory's bad, drift rate represents memory, drift rate goes down. For lexical decision, we get an increase in boundaries, an increase in non-decision time, but the drop in lexical decision drift rate, in other words, your ability to discriminate words from non-words, doesn't decrease that much relative to memory. We do fits of the model to data for memory disordered patients and controls. This is for recognition. And we're not doing too badly. So these are averages across subjects. So now, and of course, I'm skipping over a lot. All this is in the paper, and we do plots for individual subjects for each condition, et cetera, et cetera. So now this is what I really want to talk about. One thing to note, the clinical accuracy of classification is only 85 to 90%. So if somebody tells you you've got Alzheimer's, they're going to be 85 to 90% accurate. And when you die, post-mortem can be used to tell you whether you had Alzheimer's or not. But of course, after you're dead, you don't really care. By the way, did you see that announcement of that maybe your memory flashes by your eyes? Some fMRI studies got some person about to die. Activity went up. I think it's something for us all to look forward to. Linear discriminant analysis. So what I'm going to do is take the model parameters, run linear discriminant analysis on the parameters, and see if we can get a weighting on the model parameters that separates memory disorders from normals. I'm going to do 1,000 classifications in which linear discriminant analysis is trained on 2/3 of the data and tested on 1/3. So this is cross-validation. 83% accuracy, we get 83% accuracy of classification based on recognition, and 76% based on lexical decision. Accuracy is still about 83% if the system is trained on both tasks. And in discrimination, A is weighted most, drift rate next, non-decision time next. So let me show you what the results look like. We have 105 memory disorders, 57 older adults. They test in exactly the same way. And we also added 88 subjects who we test on recognition first, no lexical decision task, and they were speeded up a little bit in performance. They were asked to go fast, so it was a little bit different from the classification, but we run it on just the controls and we add the 88 subjects in a new analysis. We get about 83% accuracy on discriminating, and 83% is about the best you can get in commercial applications. So there's one from Cambridge using paired associate learning, and they get about 83% accuracy. So this is really not bad. Okay, so here we go. Here are the groups. Memory disorders plus the controls, plus those extra 88 subjects. Full discrimination is we just ran everything on all the subjects at once, we get 83%. Cross-validation is where we train on 2/3 and test on 1/3, we're about 83%. It's a standard deviation across the different 1,000 runs, repeated 1,000 times. We also did logistic regression and support vector machine to check out our classification. As I'll show you in a minute, the distributions are pretty similar they're pretty normal, pretty symmetric for the memory disorders and the normals. And so all of these methods do about the same. Linear discriminant analysis is the best method when distributions are normal and they're separated on one dimension. If we look at Alzheimer's versus mild cognitive impairment, we get about 70% correct. If we look at Alzheimer's versus controls, 91% correct, but this is pretty obvious. You can just talk to the people for 5 minutes and know there's something wrong with them. Mild cognitive impairment versus controls, 75%. Memory disorders, the total versus controls, 80%. So this is without these RTM controls in there. And somebody asked, well, what happened if you just ran for a limited amount of time, like you have sometimes in clinical studies? So we did 10 blocks of trials, and we get about 80% correct, a little bit less. And then we also were asked, what if we ran a different fitting method, and we did the same comparison with HDDM, and we get about the same, maybe a touch higher in the cross-validation. But the problem with this is it took about a week to run if we did it hierarchically. And if you're doing diagnosis, you want to just throw a subject in and run them and find out what happened. You would have to run the whole process again, which would be a week to run that. So that's not very good. All right, so now what I've done is I plotted every individual subject in the group. Here are the Alzheimer's patients, the mild cognitive impairment, the controls, and the other controls. So for Alzheimer's, 26 out of 29 are said to be memory disordered. We have 3 that weren't. Mild cognitive impairment, 52 are said to be memory disordered, and the rest, 24, are said to be normal. And these vary in their the severity of what they have. And we didn't take that into account. They were just classified one way or the other. The memory disorders controls, we got 7 who were said to be memory disorders, and it's entirely likely that some of these were in the MCI group, but these were just controls run out in the real world with a few that were caregivers of the memory disorders patients. And then our control subjects, only 7 were said to be memory disordered. We can also do this 4-way classification. So Alzheimer's, mild cognitive impairment, controls, and the RTM controls. We get about the same ones are said to be controls. Only a few of them are Alzheimer's. In other words, the classification put most of our Alzheimer's patients in the MCI group. And this is understandable because these are mild Alzheimer's. They're not the moderate or severe. So we're only picking up the ones that have just transitioned to Alzheimer's, which is the ones you want to look at for clinical diagnosis. 57 classified like this is putting the most in that. Only a few are Alzheimer's, the same number of controls. But if you look at the accuracy is about the same, doing this 4-way classification of people that are memory disordered from people that are controls. The MD controls are put here, and so this is because these subjects are faster and the model parameters are lower. The boundary separation is lower for these, so it's able to separate these out. If we now go back to the 2-way classification, we can look at the individual scores. And just note, this is straight signal detection theory. If we move the criterion, so 0 is what linear discriminant analysis says, I'm going to put my criterion to get the best separation. But if you want to be more conservative and only call people non-Alzheimer's that really have Alzheimer's, you can move your criterion down. But then you tell a lot of control subjects that they have Alzheimer's, they're mild cognitive, they have some sort of memory disorder. If you move the criterion up, you're going to miss some of the subjects that have Alzheimer's and call them normals, but you're going to have very few normals that you call Alzheimer's. So again, it swings and roundabouts. And one thing I didn't know is that they invented different words for hit rate and sensitivity. So the probability of calling somebody memory disordered when they're memory disordered is called a hit rate, and this is called sensitivity in that literature. And the correct rejection rate is called specificity. So if you turn your head sideways and plot these, you get these distributions. The dotted line are the controls, the solid lines are the MD patients, and these 3 vertical lines correspond to the top, middle, and bottom lines. And you can see how you can move the hit rate around. So fewer hits here for the patients, very few false alarms. Or if you move the criterion down to here, not a lot of misses, but there are a lot more false alarms. So this is straight signal detection theory. And it's something I didn't know, but you'll see the sensitivity and specificity. And this came up early in COVID, where people were talking about what the tests were and how accurate they were. And you see these terms floating around. And if you didn't know this, you might think it's some bizarre statistical thing, but it's just signal detection. We're also able to look at correlations among model parameters, and they have 2, the MMSE test, and there's a local SAGE test, and these correlated about 52% and correlated with drift rate. Didn't correlate much with the other model parameters. Oh, incidentally, if we use lexical decision scores instead of recognition, we only get about 73% correct. So recognition is the one that gives the big difference in this, in diagnosis. So discrimination between memory disorders and controls, about 83%, about the same as the best commercial packages. Accuracy can't be a lot higher because clinical diagnosis is around 90%. You've got to get control groups that are run in the same way and is matched as well as you can. Diffusion model fits the data well, both memory disorders and controls. For memory disorders versus controls, the boundary separation is larger, non-decision time is larger, and drift rate is smaller. So going back to NIMH used to fund a lot of people like Schifrin and Masovsky, Bosmai, people like that, me, and they sort of pulled out of all of that. We used to write a paragraph that said, oh, our work is going to have implications for clinical disorders. But almost none of that work ever was moved to look at clinical disorders. And there are technical reasons why. It's hard to get subjects, hard to get people who will test them. We were lucky in this memory disorders clinic. We have a neurologist who is very good about doing this. He's got a lot of money from other sources, so he lets us go in there and test subjects, and we do it. We pay one of his assistants part-time. So we've got this financial deal with them too. So you can get that, but getting access to patients can be really, really difficult. But as I said, we have not done anything like this to look at clinical diagnosis in the field, and it's something that really needs to be done, but I'm not sure quite how to do it. I'm going to be giving a talk to people who do chemo brain, that's cognitive deficits under chemotherapy, in a month. I'm going to try and sell that we need to do some of this kind of work, but I'm not quite sure how to do it. And then the last little bit, data quality. So we did some experiments with mechanical Turk subjects. Drew Hendrickson did most of this work. I did the modeling. We did 2 experiments. One used lexical decision and item recognition, just like the previous experiment, and measured IQ. We have 154 subjects. And the other 2 experiments had 199 subjects with numerosity discrimination tests. Some had IQ and some had math computations. Lexical decision, about 90% of the subjects were good and performed well and behaved well. 10% were erratic. Aging effects replicated. Age correlated with boundary and non-decision time, though there was a little bit of difference. Oh yeah, sorry, that's right. Age, that's what we got before, correlated with boundary and non-decision time. Drift rates were correlated with IQ. Model parameters correlated across the 2 tasks. Numerosity tests, we got similar kinds of correlations, but about 54% of the subjects were erratic. They were guessing and doing bad things. And this is about the last couple of slides. Here's a time series plot. I found this to be really useful in looking at whether subjects were regular or not. What I'm going to do is zoom down so you can see this better. This takes every response for every subject and plots reaction time across the position without looking at accuracy. So now here's a section, and what I want to draw your attention to are bad subjects. So here's the reaction time vertically. The thin line is at 0 and the dashed line is at 300 milliseconds. So lexical decision first, they're going along, the subject is going along. This is the second subject down if you can't see it. And then after several blocks of trials, they dive down and make all their responses around 300 milliseconds, and accuracy drops the chance. I'm not plotting accuracy here. Then moving to recognition, they behave well, drop down, move up, level off, and so on. This subject, the third subject, behaves well, gets into recognition of the vertical line in the middle, and then goes guessing. They can't do it. This subject, the 5th subject down, goes to guessing at maybe 150 milliseconds in lexical decision. And then seems to go up through the trial, slow down through each trial. This subject is guessing all the way through lexical decision, tries a little bit, goes to guessing, tries a little bit, goes to guessing. And then you get some good subjects where performance is stable across the whole range. Maybe this one dropped to guessing here for a few trials. This one is pretty regular. This one is regular. So some of the good subjects show stable performance. For those of you that know about time series plots and reaction time, people use plots like this to look for 1/f noise. We went back and looked at some of the aging studies that I was just talking about, and we get data from all the subjects out of 140 odd, except 2 that behave really, really well. And that's because we have our research assistants watching the experiment. So when we're doing our experiments with older adults, we have somebody going out to a senior center or a library, going into a room with them, sitting down, watching them, encouraging them, making sure they're on track and everything. And our control subjects, they do the same. If you put subjects in a room and just let them go, you can get bad data. You've got to watch them like a hawk. And I was saying this earlier, some subjects at the beginning of the semester, there are maybe 10% who are bad. At the end of the semester at Ohio State, they don't want to be in the experiment and they screw you up. So 50% of the subjects are bad, you have to throw them away. We just use them for piloting. We had, using a driving simulator, we had studies, and with our undergraduates, they drove off the road and drove across country and completely wrecked the experiment. And when you get an experimenter in there, if they're going to try that, you let them do it once and tell them not to and then throw them out. If you can observe them whilst running the experiment, data are better, but you've got to have ways of looking at bad data from, say, online studies. This whole replication crisis we have is all about good versus bad data. People have stopped worrying about bad data and worry whether the experiments are going to replicate. If they're bad data, they may not replicate. And even if they replicate badly, it's still no use to modeling. So the other thing I worry about replication crisis, it takes everybody away from worrying about new science. And it's inward looking. It's what science is good and what is bad. Go out and find some new stuff. And then you have to do power analyses and figure out how many observations you need to test models and run about the same. If you're going to do a clinical application, you really have to know this because time is limited. Okay, exactly 1 hour.
Yeah. Okay, thank you. Thank you for your nice presentation. Everyone, any questions? Yeah, Arash, please.
Thank you. First of all, thank you for your great presentation. It was awesome. I have a question about the importance of data that you talked about. Mm-hmm. And you talked about that cognitive modeling somehow doesn't have any major effect on the neuropsychological tests. I talked with some of my friends who are working in a clinic, and one of the problem is almost always they can't have a good data. For example, she worked with ADHD participants, and they cannot do good tests. And if we want to apply our cognitive models to them, we don't have good data. How we can make our models more fault tolerant to use actually in this kind of context? Is there a way?
It depends on what bad data are. If the subjects are guessing, you've got to try to bring them under control, get a task that sort of fits better. It's really, you've just got to go in and look at what they can't do. There are quite a few papers. So we have a paper in Psychological Bulletin that reviews ADHD and diffusion model stuff. And we talk about the quality of data in that. Some of the good. So if you get experimenters that can monitor the subjects, the children that are doing this, and you find tasks that are easy enough for them to do, yet will be fit by the model, you can actually get something reasonable out of it. I've been involved in a couple of projects with Cynthia Huang Pollock at Penn State, and she seemed to collect good data. We sent her a simple numerosity discrimination task. Is this number of asterisks bigger or less than 50? And the subjects seem to be able to do that, the children. And we're able to figure out which diffusion model parameters changed. But the data aren't, the differences aren't large enough to do any clinical diagnosis of ADHD from normals. We're still only getting 60 or 70% correct. So it's difficult. You've got to know what tests they can do. You've got to know how many observations you can get out of them before they start to get disinterested and spoil the data. And you don't want to, so one of the problems, we tried to do this cognitive deficits in chemotherapy twice. And one of the problems is you want to find out maybe 25% of people have deficits in chemotherapy. If you come and try to test them, guess which ones are going to decline to do it on the second visit when they're in chemotherapy? It's the ones that don't feel bad, the ones that have cognitive deficits. So you have a problem with these patients, the ones that you really want to test, declining to do the next session. So that's a really important problem. And this can happen with ADHD children as well. The ones that are on more extreme may not be able to be tested. So find a test that works, find a test that you can model, and then have people that can really monitor the children, work with them. You've got to have somebody who's relatively gifted at encouraging them and working with them, getting them interested in the task and so on. So it's you know, there's no good one answer. You've just got to have good people and select things the right way.
Thank you for your answer.
So
to sum it
formal,
up,
sorry, go ahead.
to sum it up, you said that we have to work on the tasks. So we shouldn't go that make models work with less data. We should just control the condition of the tasks and test. Am I right?
Yeah.
Thank you very much.
Let me just answer chat. Any pharmacological supportive data for parameters? I got involved in one doing hyperglycemia about 15 years ago. It was pretty funny. What they do is they put injections into both arms into the blood, and they pump in a glucose agonist that takes down the blood glucose level to 50%. And then what we found is that drift rates changed by about a factor of 2 when you did that, but not the other model parameters. So that was an extreme pharmacological intervention. Anyway, I think there may be others, but I don't remember. It'd be fun to try it with drugs, you know, all kinds of drugs. I think, oh, EJ did an experiment with alcohol, EJ Wagemakers. And the funny thing there was they didn't know how to titrate the alcohol. So they gave people, he drank, and then when he was reasonably drunk, they said, okay, this is the amount we gave. And it turned out that was only about half the amount that the undergraduates needed. They drank a lot more heavily, so they only got very small effects. Thought that was pretty funny. Okay, so what else?
Amir.
First of all, thank you very much for your nice presentation. I have two questions, one general and one technical question. My general question is that do we need a checklist for modeling in clinical science? Because when we see the papers that use models for explaining the clinical data, they may report different things, different measures, different fitting indexes, and so it is a bit hard to rely.
You've frozen.
Can we develop?
Sorry, you froze for about 5 seconds.
Oh, okay. I thought
different fit measures, etc. Yeah, yeah.
Okay. So can we develop, or is it necessary to develop a checklist for modeling in the clinical science or not?
Again, it's task dependent, and you could do something like that. I'm sure people wouldn't live to it because you've got limitations on how much time you can use different tasks are going to behave differently. You could do it for a number of standard tasks, but whether people would pay attention to it or not is another question. I think what you've got to do is you've got to find somebody to work with who will take the modeling seriously and give you access to patients in enough ways. And then you've got to watch them and make sure they can do the task. And then you've got to collect enough data to do it. And you've got to look at the data from the first few subjects and make sure everything's okay before you run, because you might want to tweak the experiment and have less observations or less difficult conditions, put fewer conditions with more observations. There are all kinds of things you have to worry about. So the checklist would have to be pretty comprehensive. And some tests that have been published, and I've been looking at these quite a lot, just aren't very good tests for modeling. I mean, you can apply the model, but just don't trust the results. And then back to data presentation. Yeah, people can produce really crappy data and then hide it behind fit statistics. That's why I want to do these plots of every subject and every condition for quantiles, something like that. I think having a standard way describing it, and my method isn't necessarily correct, the right one or anything, but you've got to do something like that. Some people, especially in the neuroscience area, just throw all the reaction times together and plot them. And that confuses differences across subjects with differences within conditions. And usually find some slower subjects and a lot of faster ones, so you get a right skewed distribution. The model produces something like that, but the model can be completely misfitting at an individual level. So you've got to be really careful. And if you're really worried about it, get their data and do your own fits and look at the data. And do some time series plots of the data like that, because data can be really, really bad. Incidentally, if you've got fast guesses, we have a paper and scientific reports that implemented a fast guessing model. So we can now handle complete fast guessing where they're just guessing at low accuracy conditions. Okay. And what next?
Thank you very much. My second question is about the interpretation of the inhibition in your continuous circular diffusion model. As you mentioned in your presentation and in your paper, the accumulation is 1 versus all. So when we are accumulating to benefits of one option, the other options are inhibited. But in some cases, especially in the continuous context, when we are accumulating to one towards one option, some other options can be also excited. So I think it's a bit weird song about in this model.
I think Philip's going to talk more about this. That's handled very naturally in our model, and we have data where we have 2 patches of brightness, and you have to respond to the brighter of them. And there we get peaks in both. So we get, the model will sometimes, it'll accumulate evidence up to a criterion from both peaks. Sometimes one will win, sometimes the other will win. And so that's very naturally handled. By inhibition, it's sort of like feed-forward inhibition. It's really normalization rather than inhibition, because we're not actually going out and inhibiting any particular thing. Noise just drives down some areas. So if you looked at the average across many trials, the peak would go up and all the others would go down below the starting point. So it's not inhibition in any, inhibitory way that you want to talk about in cognitive psychology, say Stroop effect or flanker task or something like that. It's not that kind of inhibition.
Yeah, I agree with you. Thank you very much. Thank you.
Okay, Amin, please.
Hello, and thank you so much for your valuable presentation. My question
Stop
is
saying
that,
thank you.
My question is that as you know, to compare the model comparison, to compare some models, we use model comparison criteria, for example, BIC and WAC. Sometimes we have two models to compare, and for example, the best model is a little bit lower than others, and not very, and not much more smaller than others, and then we select that one because of that is a little bit smaller. Is there any way to choose the criteria how much smaller the best model WHCs should be?
I don't know how to do that. And I talked to Jamie Young in our department, who's did a lot of the early model comparison, asked him what statistics, is there an agreed upon statistic in this literature? And he said, no, everybody uses what they want. If you notice, when I presented AICs and VICs, I presented in parentheses how many subjects were preferred by that model versus others. And I'm still not sure what to do. If a subject is better fit by one model, do you say then these 4 subjects preferred this model and these use this model and these other 8 use this model? Or if you do randomly select data and do the fits, does one fit statistic win out over another or something like that? So there's a paper, who is it? It's Wagemakers, Ratcliff, maybe Farrell on, oh no, it's Gomez and Iverson. And I'm not sure, it's on my website, probably 2006, 2007, using parametric bootstrap. So the idea is you generate simulated data from a model and then fit it with the other model, fit it with both models. Generate simulated data from the other model and fit it with both models. And sometimes you find the criterion to separate. One model is more flexibility than the other, and so it fits better, even if it's the data generated by the other model better. So what you can do is work out a goodness of fit value that then separates the two equally well. So I would say go to Monte Carlo, if you're really concerned about which is the better model, go to Monte Carlo simulations and examine the model space and see if one model is more flexible than another. But I have no answer to which model fits better.
Okay, thank you.
Then what you would do is, then you try and think out tests. So if we manipulate this, the two models make differential predictions. If you can find that, and then you find one model fits that okay and one doesn't. So going after differential predictions is a much better way than looking at, say, relative model fit.
Okay, thank you. I review your paper, non-parametric bootstrap in 2004. And another question is that sometimes with our manipulation in the task, we need to check which one of encoding time and motor execution could be changed. Is there any way to separate this parameter?
Not in the behavioral data. Then you'd go to something like EEG, perhaps, and look for signatures like that.
Okay.
Or single cell recording in monkeys might be able to separate out some of those things. But yeah, otherwise there's no way that I know. Oh, wait, there's, you might look up the Verdonk and Tuurling's paper in Psychological Review, maybe 8 years ago. They have a method for separating. It's, oh no, it's less than that. It's maybe 5 years ago. Verdonk and Tuurling's. So there's a method where they try to separate out a real model of non-decision time, find out what that is, using, I think it's Fourier deconvolution methods. But that's really all I know. And what I do, there is no way.
Okay, thank you. But my last question is that I saw some paper that explained that encoding is a sequential step with the accumulation. As you know, perceptual discrimination is a three-step encoding, accumulation, and motor. But there is some papers that show that motor execution and accumulation is in parallel, not in the sequential. I mean that when we accumulate information at the same time, it may be motor execution could be ready and sensitive to response. Do you have explained about that? It may be discard a little bit the DDM that separate each of the steps.
Well, certainly in some motor responses, you get motor preparation, and that may be related to where you are in the decision process. If you take two of racing accumulators, I think Andrew talked about that yesterday. I was on the road yesterday driving, so I didn't hear it. You could do that. We have parallel racing accumulators for monkey data with eye movements. And there you find no evidence for preparation. If you're going to make an eye movement response, evidence seems to accumulate up in these areas, and then bang, you ballistically move. But there's no evidence for motor preparation in those areas at all. That seems to be an all or none. So it depends on the system. But I bet you could then have leakage from the evidence accumulation process to the motor system and model that. So that would be what I would try first.
Okay, thank you so much.
Okay, Robert.
Yes. Hello, Roger. You mentioned in your talk a rather subtle point, which is that as opposed to like a signal detection framework, the drift diffusion model is decisively falsifiable. Can you elaborate a little bit on what this means?
I've got a paper in 2002. So I submitted a paper, and at this point, the Robertson-Paschler paper had just come out that said, oh, models, the initial draft said models aren't falsifiable. So John Wicks said, who was the editor, said, if you can address this, it would be really cool. So what I did was generate some fake data sets and then fit the diffusion model to them, and found it couldn't fit most of the fake data sets. So if distributions shift and don't spread, and you only allow drift rate to change. So if with difficulty the distributions shift, the model can't handle that. If the distributions are not right skewed in the right way with an exponential, roughly exponential tail, if the tail is higher or lower, it can't fit. If the reaction time distributions are normal, it can't fit. So there are a large number of signatures like that. Say errors are much slower than correct, shifted up or shifted down, the model can't fit. So there are a large number of patterns of data that the model can't fit. And one of the amazing things I think is you keep running experiments and you keep getting right skewed distributions that mainly change where the shift in the tail is difficulty changes across a wide variety of tests. So the models do seem to capture this important regularity in the relationship between accuracy and reaction time distributions. And that's why I push analysis of distributions all the time, because they're the ones that really capture whether a model can fit or not. How's that?
Okay, thanks.
Okay, Hassan.
Hello. I had two questions. The first is that is about your continuous model. I want to ask that isn't it a bit strange that we have in your plots about accumulated evidence, we see that there is a trough near the answer, and isn't it strange that the person has accumulated less evidence near the true or near the near his choice?
Yeah, I'm not sure what to say. So on a different trial, they won't accumulate less evidence. If I let the model not normalize evidence, then probably evidence away from the peak would be kind of flat you wouldn't get the large negative going. You get some, but not as much, and evidence would grow more quickly. So yeah, it's sort of an issue. And if you believed in population codes and neural processes, you might put a limit where activity can't go below a certain limit, and then it would get squashed at that limit. And that would change the model a little bit in the behavior, but it'd probably fit in the same way. So if you want to modify it to be more neurally plausible with activity not going highly negative, that certainly is possible. But then you'd have to refit and check everything worked in the same way.
Yes, yes. Maybe we would expect, we expected that the correlation parameter should be higher than to make this one model thing, but the recovered parameter is not. Yeah.
It's a fitted parameter. The range parameter is a fitted parameter.
Yeah.
So it's what the model tells us.
Yes, yes. My second question is general. I wanted to ask about your perspective of the future of these cognitive decision models, and maybe if there is any, you may mention recent works, interesting works or trends related to these models, like your last work about classification and clinical diagnosis. That was very interesting. Are there any recent trends or maybe possible interesting in future?
I think applications, if you can get access to a good patient population and tasks that make sense within that population, I think there's a lot of room for trying to impact a wider area than just mathematical modeling. I think Philip and I, Philip Smith, we're doing this continuous modeling and multi-choice modeling, especially confidence judgment models, are areas that haven't been worked on very much. So I think if I look back to when I first developed the model, hardly anybody worked with these models. There were people doing random walk models. The diffusion models sort of sat around for years. I was doing little bits and pieces and doing work in memory and implicit memory and all kinds of other things. And then it sort of took off. I think in the same way, continuous models and confidence and multi-choice models, they're more difficult to work with because you've got to constrain the model in ways. The models are less constrained, I think, in some ways. You've got to find data that constrains. But I think those are areas that really need to be worked out. And I'm kind of surprised that people haven't done that. And I think the reason is they're difficult. So everybody has their own little version of a two-choice model. And let's do optimality now. Let's apply to this test. Let's do this. Let's re-examine this. Let's re-examine that. And those are all relatively easy because the models and the fitting packages are all there. These other domains, like Philip will talk about, are new and nobody's really worked on them before. And there's a big startup cost, but once you get into them, there are so many things that can be done. So I'd say applications and other things. I think reinforcement learning is in the same state. There are various models around. They've got to be shown to be work with individuals. Simpler models and better fitting methods have got to be got. But I think that's a domain that works. But in other areas like memory models, we once tried to look at individual differences and all the model parameters do the same thing and there was no way to tease them apart. So you've got to have a model that will do individual differences and then apply it and see what happens. Or you've got to find domains that haven't been worked out.
Thank you very much. In fact, Philip Smith presented before you in our morning. Yeah.
He did? I thought he was presenting afterwards.
No, it was before you, and yeah. Thank you very much.
Okay.
Okay, Roger, many thanks again. It was our pleasure to have you in this mathematical psychology school.
You're welcome. It's nice to be able to talk, but I really miss not being there in person. Because it would be good to be able to talk to you and interact and see what your faces are doing and the disgust or happiness on them or whatever.
Yeah, thank you. Bye.
Sure. Bye-bye.